All right. Hello, everybody. Welcome to an earlier morning expert hour. Really excited to have this expert hour because we haven't had one since, I think, November or December. So I think this will be a really good opportunity for everybody to learn from a real world structural engineer and projects that he's actually worked on. It looks like we have quite a few people still just coming into the waiting room. But for the sake of time, because I want to make sure we have as much time as possible to speak with David, let's go ahead and get going. So as you guys know, this version of Expert Hour, we're going to be talking about heavy timber engineering, if I could talk, with David Hourdequin. So we got to go through this one. As always, you guys have probably heard it 1,000 times about ClearCalcs.com. ClearCalcs is a cloud-based structural calculation software combining powerful FEA analysis with, hopefully you guys have seen, easy to use design tools, wood, engineered lumber, steel, cold form steel, concrete, looking to be more accurate, eliminating wasted time, and available everywhere. So the two hosts, and then we'll definitely introduce David. You guys have probably spoken to us. We've got Laurent, who's a professional engineer and also our North American engineering content lead. All these new calculators that you guys have seen being pushed out in the past few weeks, he's leading that work, which I know from my end is super exciting to see. And then myself, I'm our director of customer success. So here to make sure you're successful in ClearCalcs, whether it be training sessions, help content, anything like that.
All right, and I think I'll take over from here. I get to be the lucky one who introduces David. First of all, David, thank you for being here with us today. Just a little bit about David here for everybody else who hasn't had the chance to meet him yet. David has spent about 60 years in the construction industry. So since he was in high school, always had a connection to it and learned a lot from it. Right now, he's the president owner of Rémy Co. And he's doing a lot of engineering, especially with heavy timber engineering. Before that, about 20 years in structural engineering and construction management. And then the last 25 years focusing on his real passion, which is heavy timber engineering. And through all that, I think he's learned a tremendous amount. He's touched about every single part of the construction industry. And so he's now sharing his knowledge, and we're lucky enough to have him here to share his knowledge. And bit of a cool thing that just happened. David recently released a new book, actually, on consulting engineering success, and it is available right now on Amazon Kindle. Encourage you all to check it out. I just had a read of it over the weekend. It's a very short read, very well written. It reads really well. I think some of the cool things that I found, how oysters can help you find new customers. I thought the four-way test, which is actually from the Rotary Club, and very, very simple yet useful guide, I think, when we've got to make tough decisions here. And then I think the one that we've probably all identified with at some point in our lives, or perhaps right now, overworked and underpaid. It's actually the name of a chapter. So I'm sure you all identify with that. Encourage you all to take a read. And I think just overall, the cool thing here, David, has been extremely transparent, vulnerable with this book. And I think same thing with today with the presentation. And then we had a chat before. Feel free to send your questions, even if they're hard questions, in the chat. David's is an open book today, and he's here to basically help out, share his knowledge. So encourage you to read the book. We've got David here today. Take advantage of it. Ask whatever questions you have. We're going to go over some projects that he's worked on today. I think it's going to be really exciting. And one last thing here, if you want to ask questions, I'm talking about that. At the bottom of your screen, you should be a little chat window here. Just type your question in here, and we'll be going through these as we go. Don't worry about interrupting or anything like that. We'll make sure that your questions come through, and we'll be more than happy to have perhaps a Q&A, or we can do it as we go as well. we'll see how it goes. All right, and with that, I think I will hand it over to David, who's going to start speaking to us today about specifically church projects that he's worked on that really, I think, looking at the pictures that David sent before, they really show off the capacity of heavy timber here to make beautiful, beautiful structures, make efficient structures, and also give us all a cool engineering challenge once in a while. So over to you, David.
Okay, let's see if we get into share screen mode here. If I don't flub this too badly. And where are the photos down here? Okay. All right, so pardon me. Got all these selected. And we're going to go to full screen. So I guess everyone can hear me okay. I see up on the screen that I'm the guy that's doing the talking. So I just want to welcome everyone. It's so great to have you all here and to talk about my favorite subject and my passion in life, vocationally at least. I often tell people if I had to choose between working on a hobby project and doing timber engineering, I'd rather come in here and design a truss and then go home and do the other stuff. So that's kind of how I feel about it. This particular job was one that was a lot of fun for me. It's at Belmont Abbey College over near Charlotte. It's called St. Joseph Adoration Chapel. And this came to me courtesy of Josh Coleman. I hope Josh is on today. I think he had planned to attend, but interestingly, Josh has led me into some really fun and exciting projects that architecturally, it's not about size for me. It's just about exquisiteness, I think, in the design. So I'm going to go through these slides and then we'll come back and talk about some specific subjects. And if you have any questions, I'm going to ask Laurent to be the moderator. Just put them up on the chat box, and Laurent, you feel free to interrupt me anytime, and we'll deal with whatever anybody has. But if you can hold off till I go through it, maybe, and then we'll go through the questions. Maybe a project at a time might be a smoother way to do it. So without further ado, let's take a look at this. Interesting thing about this structure is the grid framework here. These are all 6x6s that are connected, interconnected here. And you'll see the inside of it, all glass everywhere. The grid is 5 feet by 5 feet. And when I started on this project, it reminded me very much, I think it's Duane, the architect from Arkansas. The interesting thing about Duane's work, if you can see my pointer, is up here where timbers intersected, he would always have a hole. And so I guess it was a piece of square tube or something like that that was in there. But I always liked the fact that the light passed through these holes. But I couldn't talk anyone to doing it on this job. They had pretty much decided what they wanted to do. So let's see what else we got here. Another close up. I love ecclesiastical lighting, so pretty inside the chapel. It's not a very big building. I don't know, maybe 20 feet wide, well, probably 25 feet wide, maybe 40 feet long, not big at all. And there's the kind of assemblage of it. And these are this is a really interesting truss system because it's like 2 parallel cords instead of a scissor truss. Not uncommon, but a little bit unusual. You don't often see truss configurations looking like this.
I'm supposed to send you details, I forgot.
Hey, Josh Coleman, I see you. Speaking of, we should probably let Josh have a few words here when at some point. So anyway, I don't know what happened to the, I hope I have the drawings. So because this chapel is all glass everywhere, the only thing it had were a couple of closets and restrooms. This is up at the front corner, and there are restrooms on both sides. And so, with all the glass, we couldn't get enough out of the shear wall, so we put diagonal tension rods in it. And I took this photograph a couple of years ago, and I went over there, and this one was slack, and I had to call people up and remind them, you got to keep those things kind of snug. Fortunately, I think this was the way it was installed to begin with, because none of the glass had cracked. So thanks be to God for that. Here's another shot. These are all swaged fittings. Josh found these, and they're connected to steel brackets down here at the bottom and up at the top. I thought it was a pretty good bracing system. And these are in both directions. And this is the lateral force resisting system for the chapel. So let's go back. And Josh, I thought I had a couple of slides, but I don't. But anyway, what I wanted to let's go one more. What I wanted to share principally was that wherever timbers crossed in here, timber links connected the discontinuous pieces. In other words, if there was a continuous piece, let me see if I can find another slide. Yep, sorry about that. Don't mean to make you dizzy. If there was a continuous piece in here, like right here, that was fine, but we needed to find a way to connect these two pieces here that were interrupted by the bottom cord of the truss. And same thing within the truss cords. Everywhere there was a discontinuous piece, there was a timber links across that. And it's if you can look that up, I'll leave that to you on your own. I thought we had a slide of the connector, but for some reason it dropped through the cracks, as things often do. But anyway, a timber links is a tensioning device that has a piece of all thread to two, looks like sleeve anchors with pins at each end, and the pins are expansion pins. So once you put it together, you can crank on it like an old time car jack and tighten the pins up, and it locks the joint together. And so if you put, my theory was in doing this, if you put a pin in the center of the timber, there is some inherent moment resistance because the timber links can take tension. And of course, the fibers on the nearest side can take compression, whichever side it is. So there were quasi moment connections in every connection in here. And I thought that was the most interesting part about this. I will say, of all the projects I've ever done, appearance wise, it's certainly one of my favorites, certainly in the top 5 for sure. And Josh, if you're on and we can hear you, if you'd like to add a comment, chime in. There you go.
Hello?
Yeah, we hear you, Josh.
Yeah, all right. Yeah, I would just say this isn't quite structural analysis comment, but we put these whole wall bents together on the ground, laying flat, and then picked them up with a double hoist crane. So you could like basically lift it horizontally and then rotate it in the air with the two hoists, two different cables. And then we had to thread it down through between the trees and then turn it 90 degrees. And but the whole time, you know, once you got vertical, it was so stable. Of course, it was a little dicey going from horizontal to vertical. But yeah, and then just that was the key to weaving these timber links together on the basis that like you couldn't assemble this vertically. It had to be all kind of pieced together on the ground, and then once everything was locked in and the timber links were tightened, and then we could stand it up and fly it in.
Thank you, Josh. And just a terminology for those of you that are not into heavy timber engineering or timber framing, this post and the adjoining truss right here all the way across the other side is typically we call a bent in timber framing. And so what Josh was talking about pre-assembling is this entire frame laying flat down and then picked up with a crane and set in place. And then you set the next one, and then you set the interconnecting timbers. And I guess, Laurent, back to you. There were some questions maybe that you all had about this that you'd like to ask.
Yeah, so just a reminder, if you guys have any questions, you can put them in the chat box, and also just unmute yourself and ask them out loud. But you know, we like to keep it casual here. One question I had for you, David, actually, with the glazing here, and you've got some pretty complex trusses here. How do you consider deflections here to make sure that they don't get transmitted to the glazing?
Well, when the glass breaks, we just try to use smaller panes of glass. this truss is so inherently stiff, it was incredible. And usually when they put inset glass, Josh could probably speak to this better than I can, but when you inset glass like this, I'm pretty sure it was all really heavy plate or safety glass. And there is some tolerance built around the frame. In other words, the glass doesn't fit perfectly at the timber. It's probably an 1/8 or 3/16, maybe even a 1/4 of an inch shy in each direction, and little moldings hold it in place that are caulked around the glass. Josh, you have anything to add to that?
Yeah, as far as I know, can you hear me?
Yeah, you're good.
Around. Yeah, as far as I know, it was kind of like a storefront window type detail where there was the C channel and then a complementary one, so that there was a good bit of, like, well, it's all relative, right? You know, there was enough tolerance within that frame that it was a little squishy.
Thank you, Josh.
Yep.
Anything else, Laurent?
I like the, thanks, Josh. I like the squishy factor. That's a very underused engineering term, I think.
Squishy is a good term. That's what timber does when it gets to decayed. It becomes squishy. So
that's right. We've got a few questions here. One from Jim Fanjoy. Jim, I wonder if you want to unmute yourself and ask it out loud, or I can read it if you want.
Yeah, it took a second to find the unmute. I was wondering, it looks like there's a lot of squares in that truss and not a lot of triangles. Are some of those are most of those null force members that just keep the glass from moving around? Or like what holds the roof up, I guess?
Well, actually, this is not technically what we might call a true truss, which is an assemblage of triangles to span some distance, I guess. One definition. It is essentially a moment frame truss. It's every connection is a moment connection in it, and so it didn't need to be triangulated. It was designed with moments in each direction. So I hope that answers your question. But yes, I mean, good observation. It's not triangulated, and it was done like that because the architect wanted to see it this way. And so the only way around this, when you're going to induce moments in the truss connections if you don't triangulate it. So we had to deal with those inherent moments. And that's what those connections were doing. Like right here, I believe this member would have analogous to be in the plane of the truss. And then this was a crossing member here. All the crossing members were connected with these timber links, which pre-tension the joint. Now, some would argue that's not reliable, but I mean, this structure's been up for a long time, and the serviceability factor is excellent. So I think bottom line is we guessed correctly. That's about all I can say. Anything else?
Thanks.
Yep, sure. Okay, shall we go to the next one, Laurent?
Yeah. David, we just had one more question here. There are actually kind of two questions about connections here. So we've got Geo, hey, it's been a while. And Ray, so Geo's asking if Timberlinks is a kind of a product or if it's a method. And then Ray asking, on top of the Timberlinks, did you also have some traditional mortise and tenon joinery in there as well?
If there was, there wasn't much of it. Maybe some auxiliary screws. I don't remember. It's been 20 years, but Timberlinks is the proprietary name of a particular kind of connector, and it's spelled Timberlinx, Timberlinks, and you can look that up online, and it'll give you all kinds of design data for it. It's an incredible device under the right circumstances. I've spec'd thousands of them. And there's just nothing else that'll do the job quite like they are, where they fit in with the structural concept.
Thank you, David, and thank you, Glenn. That sent a link to the website as well. So if anybody wants to check it out in the chat. And Glenn has sent the link.
Okay.
Okay, David,
All
I think I'm ready to go to the next one.
Okay, this is. Let me get these all selected here.
While you're pulling that up, David, there's actually just one question that came in from Caleb. Really
Sure.
quick on that last project. He was wondering if you calculated the moments individually at each of those joints, or if you used a rule of thumb there.
No, they were all, it was put into a finite element analysis 2D frame and done that way. I have to confess, you younger engineers that are coming along that are learning 3D analysis, I think that's kind of the way to go, but we can get off on a tangent here philosophically, but I've always tried to keep the analysis simple and conservative. So almost always I use 2D frames, and I just take the worst case situation and I analyze it, put the gravity loads and wind loads on it, look at all the load combinations and pick the worst stresses, and away you go. So the answer to the question, that's a long way to answer the question. Yes, they were analyzed, and that's how we came up with the capacities we needed. And it turned out that the timber links had more than enough capacity the way that we used it.
Thank you, David.
Okay, this is Horizon Community Church. This is really a fun project. Dan Kaiser may be on here. He can add some comments. I did this with Harmony Timber Works. Gosh, I don't know how many years ago, and this was all glue laminated. Every component in here was Doug fir glue lam, and it was probably the largest glue lam job I'd ever done. And so I asked Dave Fischetti. Some of you may know Dave. He passed away here a number of years ago, but he was probably the United States preeminent glue lam engineer. And Dave lived not too far from me over in central North Carolina. And I asked Dave if he would like to be the engineer of record on this and let me be the idiot doing all the calculations and scaring everybody to death. And he said, sure, he'd be glad to. And he had a few comments that were good, but by and large, everything worked out just fine. This is in the in what they would call the narthex. This is a community church in Cincinnati, and interestingly, this wall was curved, but everything in here is square. So these are like chord segments, and you can see the arch members in here, and then back here in this area, very at the far end, you have intersecting gables. They're always a lot of fun. Because the boundary of the intersecting gable, both the interconnection between the trusses and the trusses themselves, all form a tension ring for the load in the center of the interconnected gables, because they've got to go somewhere, and so they're resisted by these ties in both directions. So let's just continue on here. It's another shot. This is the intersecting gable up in here. You can see it coming to a peak. So when you apply a vertical load at the peak, each one of these hip members wants to push the column out, and so you've got the bottom chord of each truss acting like a tension ring all the way around that square, holding everything together. There's another shot of it. We haven't gotten to the good part yet. Whoops. Okay, more of the same. This intersecting gable is in the church sanctuary, right over the center of the nave. You've got a transept going to the left and a transept going to the right, and the assembly area back behind you. And you can see these arch members here. This is just a typical truss that was in there for the rectangular portion. However, out in here is where the interesting part of the design was. You've got a curved truss here. You got a curved bottom chord truss there. Again, it's all glue lam, and we'll see close up with these connections. But there are 1-inch tie bolts on steel knife plates. The plates are not visible. In this case, I think they were either 3/8 or 1/2 inch thick, and the plates are in slots in the timber, and we call them either knife plates or kerf plates in the timber frame industry. And so you had them here, and you had them crossing out here, and in this section right at the king post, we had cross plates going up in the king post, and then a knife plate going in each of 4 directions. So that steel assembly is socketed up in there. You can't see it, but it's the one that's doing all the work. And the interesting thing about this job was that right here, where this intermediate web member is, that vertical web member, that that one and the two on the far side of the intersecting gable define the corners of a 30,000 pound cupola. That's 15 tons, folks. That's like, well, what's that 10 Chevrolets sitting up there on the roof trying to push things down. It was a pretty challenging thing to run the numbers on, but and I've got a shot of the exterior. You can see that steeple. It's pretty incredible. They gave us some relief. They were originally going to do it all in brick, and I think they wound up doing some stone veneer, but it didn't help much. Originally it weighed 45,000 pounds, and they figured they took 15,000 pounds out of it, and so left that in it. So let's see what else we got here. This, you can see the bolts up here in the knife plates at each end, especially right up here at the king post. That's what this member is. That's the king post of the truss. For those of you that don't deal with truss terminology, I know a lot of you typically do mainly structural steel and concrete and maybe light wood framing. Church service there. There's another shot of it here. That's a better close-up, and you can see how everything is bolted together on these knife plates. The photo looks a little fuzzy to me. It probably is to you, but you'll just have to forgive me for that. And then this is back in the main area. I think this is about 45 feet across from left to right, and the arched intersecting trusses were 65 feet long or something like that. There's a beautiful shot showing that intersecting transept. Whoops. So there's the assembly area again. Let's get out here. I want to show you some. So there's the steeple right there. This is the little gem that weighed 30,000 pounds, and at each corner is where it came down on that vertical web member of the truss. And I can't remember exactly how that was framed, but there was a piece running up the rake and down the other side. So I guess for all practical purposes, it was this part of the truss was loaded with that vertical load, that trapezoidal load going across that face and going across this face. And all of these loads just work themselves down into each of the four faces. But it was a challenging little design. So let's go back to the middle. We'll stop right there. So any questions? Oh, by the way, the tension in these trusses was about 70,000 pounds, I'm thinking, something like that. How many bolts we got in here? 2, 4, 6, 8, 10. So you know, that's quite a few. Probably at 4 or 5 kips, so 50-60,000 pounds of tension at least in that bottom cord. Another thing, while I'm thinking about, I want to mention, when you're dealing with glue lams or any other curve member for that matter, but particularly for glue lams, you have radial tension stresses here. As that member is under tension, it tries to straighten out. And when it tries to straighten out, the laminations of the glue lam try to come apart. And so you always have to check these arch members that are under tension for radial tension. So questions, Laurent?
Yeah, thanks for showing that, David. That's a super cool one. And I like the Chevrolet analogy with the steeple there. We've got a question here from Gio. Could the base of the steeple be a truss as well, or would that just screw things up?
Yeah, I don't see where that would be any advantage, particularly. Those walls of the steeple were like shear walls as far as wind loading is concerned, which, by the way, put an interesting twist on the analysis, because that wind load had to be generated into this frame. Interesting thing as I talk about that, about wind loads, is that the allowable stresses under wind load in any load combination, including wind, can be increased by 60%. So seldom, I'm not saying always, but seldom does it control the design, except for maybe top chord truss stress reversal in super high wind loads. You get into 160, 170 mile an hour wind zones. And if you've got a simple gable truss that ordinarily the top cord is in compression and the bottom cord is in tension, all of a sudden now the stress is reversed completely and the top cords are in tension and the bottom cords are in compression. So you've got to take into account that complete stress reversal and tension and compression reversal. But here, I think just the simple four-walled structure was probably the easiest. And it wouldn't have, if we had trussed anything up in the steeple, it wouldn't have changed any framing down here. So, you know, kind of pay your money and take your choice.
Thanks, David. One thing that I'm wondering, I'm guessing I'm probably not the only one on this call who's never specified a curved glulam member before. And you mentioned about radial tension and that being a consideration. Is there anything else that, say, if I wanted to specify a curved glulam the first time, I should be aware of or I should consider when I'm specifying it?
Well, if you look in the back of the NDS, the most important thing is the layup. And for example, if it's a flexural member, you want the best fibers in the bottom of the glulam, and so there are, if you look in the NDS, you'll see that flexural members have different load combinations than axial tension members. For example, axial tension members like this one, the lamination quality is balanced and symmetrical around the center line. So that's one thing to learn. The other is that, and the beauty of this, and I'm gonna slide off into an adjacent area, but when you're designing kerf plate connections with bolts or pins, you can use steel pins or bolts, either one, like these are. If you have green timber, you cannot put two rows of bolts on a common plate, because as the timber shrinks, it will split either down one of the rows or in between them or something like that. And so the capacity of each bolt has to be reduced to 40% of its nominal capacity. So that's a horrendous reduction. And so to get around that, maybe in some cases you could have an isolated strap at the bottom and another isolated strap at the top. That way the straps could float as the wood shrinks. But if you have one solid plate with two rows of bolts, then that's a no-no in green timber. Now, with glulam, it has an inherent moisture content much less than that, 12% max probably. And so when you have a timber that has a moisture content of less than 19%, then you can put two rows of bolts in here. Now, normally you wouldn't put more than two rows of bolts in heavy timber, but in glulam you can put more rows than two. The most I've ever done is 3, but in order to do that, the distance between each row has to be 5 inches. And then you have to have 2.5 inches of edge distance out to the side of the timber. So if you were putting 3 rows of bolts in this glulam, it would be 15 inches deep. And I think, if you're embarking in the glulam area, I'm trying to remember the name of the company, Structural Wood Systems. Structural Wood Systems in Evergreen, Alabama has got a staff of engineers and people down there that can help you with something like that. So if I was getting into this for the first time, I would have them kind of look over my design. And then once you put it out for bid, they're probably going to be one of the bidders. Now that may give them an inside track, but in this game, I'm just so against conventional design, bid, build, as opposed to design, build. I think you ought to put everybody together and then do it. Anyway, got a little far afield there, but one thing led to another, Laurent. Hope that answered the question.
It did. And honestly, I think we all appreciate the insights here. It's really, really cool. One more question here from Hieronymus. He's asking, what does the analysis for the additional radial stresses look like? So would you take the orthogonal tension and then add a bending component just because of the eccentricity? And does that affect the connection design?
No, I mean, when you're checking for radial tension, there's a fairly simple formula in the in the timber construction handbook. Let me see if I'm not going to look it up right now, but the timber construction manual, 6th edition. If you look up radial tension in there, it'll give you the formula, and you just simply put in the radius of curvature and the size of the member, and that formula will give you a value that has to be less than a controlling or limiting value. I think that's about as complex an answer as I want to get into at this stage of the game.
All right. Thank you, David. I was going through the NDS really quickly here, seeing if I could find a formula, but I didn't make it in time. So it is in the NDS, I believe, and you'll be able to check out that formula. Thank you, David. I think good to go to the next project if you're good.
Okay, I'm good. Let's see. That one is St. Thomas the Apostle. Josh, if you're still with us, I'm sure you'll have some interesting things to say about this. This was another fun project with Lancaster County Timber Frames. Well, come on. Oh, here we go. All right. I don't know who that is, but they're having fun. So I'm going to come back to this slide. This is actually a tension strap, and I'll explain it here in a minute. So let's see if I can get to, okay, here we go. So this structure had 3 square areas that were co-joined or had common walls in an elevated stack, and the intriguing thing about it was that this the top plate up here is a tension ring. You can see the rafters all going down here. They're connected at the plates going around it, and they're trying to push that thing out. If you imagine a load down at the peak, it just wants to spread everything apart there. So up at these corners, you have to put straps around the corners or knife plates inside the timber or something to take the tension. And the way that you do that, I just divide up the forces into summarized into 4 components. I don't worry about this. This rafter is going along for the ride. It's the ones at the hips that define the tension ring. And so when you put all the design loads in this has a certain compression in it that gets transferred into this corner, and it's trying to shove the corner in a direction parallel and collinear with the hip. And so you can divide that up into components, so you can design a strap that goes along the plate in one direction and the plate in the other direction to take that tension. And so that was the intriguing part about this. And so we start cascading down through the structure. So you go from the tension ring, and then you've got these posts in here. Now this gets laterally stabilized later. Don't worry about the racking. That was all done with shear walls. So you come down here, and now we've got another plate line around here. Well, with the loads on that now is a compression ring. You know, you're pushing up on it, and so it kind of works in reverse. And then down here you've got another tension ring, and right there is that strap that he's working on, I think. And it's a pretty hefty piece of steel. Usually you'll find that 1/4-inch plate steel can be used for this, and I'm not sure why that's so far apart. Normally, you know, if you can, you try to get them up in the middle. I'm sure there was an aesthetic reason for this. Nothing wrong with it, but you can see the top of the corner post cut off here to have a housing to engage that rafter, so that thrust goes into the post, and the post is trying to come out of the screen and toward your left, and these straps keep everything retained. And that handsome fellow looks like he needs a break. That looks like hard work to me. Here you see the strap in place going around this tension ring here at this level. And I think this is probably one of the most exquisite joints I have ever seen. Josh, my compliments to you. I showed this to Dan Kaiser earlier today, and he said, I have got to try to do that. So any of you that, you know, are good at geometry, maybe you could construct this freehand. Josh will, for $8, Josh will send you the secret formula. So there's another shot. St. Thomas the Apostle, beautiful shot looking up through the core of the intersecting cascading squares. There it is, completed. Absolutely beautiful. I can't take credit for how pretty any of this stuff is. I tell people I'm like I am to engineering what an orthopedist is to medicine. I just work on the bones of the building and I try to keep them from breaking, and that's what an orthopedist does. There you get an idea of the volume. Josh, anything you'd like to add? Josh, you there? Hello.
Hi, can you hear me?
Yeah, we can hear you.
All right, wonderful. So yeah, I would just, it sure was a lot of fun to do. David, maybe you can flip back one slide, like a longer shot. So you can kind of see, yeah, actually that was perfect. So we actually assembled the upper cupolas on the ground, and then the lower hip rafter, you see that has kind of an overhang. We set each of those hip rafters individually, and then we're able to kind of tether it down on the rafter tail outside and just hold it into position. So once all four hips were just sort of floating out there, and then we lowered the whole cupola down and nestled it into those hips. So a lot of precision fits there, but everything went really nice. And yeah, that was me in that photograph, putting those lag bolts in that metal strap. I think there was 15 on either side. It was let's just say it was a long day of running that impact gun. But yeah, this was a fascinating one because they didn't want any interior columns, and coming up with a system that could support all those layers without any interior columns. It was a lot of fun. And the pinwheel, I call that the pinwheel joint at the peak. Yeah, those always work out really nice, and it's sort of in the vein of that reciprocal framing idea, which is a whole nother world. But yeah, this my little contribution to that.
Thank you, Josh. I'm just reminded to this point that doing one of these projects is just really a team effort, and I'm just sort of the idiot guy in the process aesthetically, because architect gets a hold of this, and then a contractor gets a hold of it, and then they turn to people like Josh at Lancaster County Timber Frame and say, pull this together for us. And so if you're the structural engineer working on one of these, the aesthetics are generally worked out for you. Now, as you gain experience, you'll have some pretty strong thoughts yourself. Excuse me a second. You'll have some strong thoughts yourself about the aesthetic side of things. But ultimately, my thing is I'll suggest what I think is a good alternative, and then and after that, it's up to the designer, like Josh or Dan Kaiser or somebody, to say, no, we want to do it this way. And the owner says, no, we don't want to do it that way. And that kind of reminds me of a chapter in the book where I talk about cautionary notes, is that sometimes a client will want you to do something that you just don't think is a good idea, but you can make it work structurally. And so I think it's important to forewarn a client and remind him on the drawings of the decision he made in so many words. In other words, if it's a situation that may be problematic, point it out right on the drawings, that this condition could be problematic, maybe hard to maintain, maybe impossible to weatherproof, whatever the circumstances are, where it ran counter to your own good judgment, then I think you owe it to yourself from a liability standpoint, and also to the client, to point that out again, black and white, big, bold, square outline on the drawings, and we do that quite a bit. Any other questions?
Thank you, David, and that was really cool. And thanks, Josh, for bringing in some more insights here. And cool to hear that you're the lucky guy in the picture with the gun. We got another question here from Hieronymus. Hieronymus, if you want to unmute yourself, maybe you can ask it yourself, or I'm happy to repeat it. Oh, he's at the office. No problem. So Hieronymus is asking here, the pinwheel joint, did you use any kind of connection in there, or are these purely just bearing on each other?
Those are all toe screwed from above, right, Josh, as I remember?
That's right. Yep. So they all nest into each other, and then once everything's planed out, then you can screw around in one direction. Then we usually go the opposite direction so that each member is screwed into the one next to it in both directions.
So we have 2 toe screws in each member looking down on it. One goes down to the right, one goes down to the left in each joining timber. So is that right? As I recall. Yeah.
That's right. Yep.
Okay. What else?
Question for you with the analysis here. I think you mentioned previously you prefer to keep it simple with a 2D frame analysis or something like that. Obviously, this is quite a, it's not in 2D. Analysis of something like that with a tension ring, then the compression rings. Did you do this by hand? How did that look like?
Well, you could do it easily enough by hand. Just put a, you've got half the load going into this diagonal and the other half going into that diagonal. So you divide that into 2 components, and you could just do longhand calculations. You put a point load up here. You got some uniform load on here that doesn't amount to a whole lot, and just take 2/3 of the load and put it, I guess, or third. Anyway, whatever it is, and you can then just using what am I trying to say? Won't come to me. Anyway, yeah, just simple statics. You can determine what the compression is in this member, and it will have a horizontal and vertical component, and you put the vertical component or the horizontal component in, and there's your tension ring. The vertical component is taken care of by the post, and the bird's mouth, this member will have a notch in the bottom of it. And of course, to hold this member to the tension ring, you have to screw it down into it to resist the forces that it has in it that want it to slide outward. In other words, if you don't restrain this diagonal hip member with screws to the post, then you can't develop the tension. So, but no, I don't do a frame analysis on that. And if you stop and think about most structures, it's easy enough to come figure out a 2D frame within it that you can analyze. Now, I know the results are a lot more sophisticated in 3D analysis, but and God bless you for doing it. I just, a lot of these small structures just don't have enough fee in them to do a super sophisticated analysis. I mean, if this was larger, more complex, I mean, you wouldn't dream of doing it in 2D analysis, but for simple structures like this, I just don't see a problem with it at all. And I think this is a simple structure to me.
Thanks for sharing. I think this would have been cool to see and to hear about when I was taking my statics course in university and learning a little bit more about this is the real world, how it works. Really cool.
Let me just make a comment about that. The first time, I don't know how many of you have gotten involved with common wood framing and Simpson connectors, but when I first entered into that world, I would look at every component and I would say, well, this one needs an L34 and this one needs a L32 and whatever it was all around the structure. And I might have 8 or 10 different straps around a roof, and I put that job out, set of plans out, and the contractor got a hold of it. He says, "Are you nuts?" I said, "What do you mean?" And he says, "We'll never get all those in the right place." He says, tell me what the worst load is, and that's what I'll put everywhere. And I said, "I get it." So there you have the message. It's like, in a simple structure, take the worst case and apply it everywhere. I know Jim DeStefano isn't on the line, but I remember just a quick aside with snow loads, and I would go to great details to analyze the fraction of the ground snow load in a roof system. And Jim says, I always just put the ground load snow load up there, all other things being equal, because he said sooner or later you're going to have drifting loads and you're going to be right back where you started. And he's exactly right. So I think it's important, if you're doing small structures, if you're not doing high-rise buildings or bridges or something like that, you need to learn shortcuts that by hand you can either check your computerized calculations or just do it by hand. And often you can do a truss longhand quicker than you can load the data into a finite element analysis frame. Go ahead, Laurent.
Thanks for sharing, David. We got one more question here from Glenn. Glenn, do you want to come on if you would like to unmute yourself?
Sure. I was just kind of curious about if you can hear me, the lateral system that you use for these heavy timber structures, is it do you connect like sheathing to the truss frame, or do you use intermediate like joint or studs, or how do you kind of analyze or design for the lateral in a structure such as this?
Okay, well, this slide is a good illustration. So it may or may not apply here, but normally these timber frames are decked, I would say more commonly with 2x6 tongue and groove sheathing. And as you all know, it has a limiting a diaphragm capacity of about 70 pounds per foot in allowable stress design. And so sometimes you can accomplish it with just straight decking, provided that you have other structural auxiliary bracing to counteract lateral load, like diagonal bracing or diagonal members or something. Otherwise, you have shear walls. And if the shear gets too high in these decks, then they have to be overlaid with structural wood sheathing to develop the diaphragm capacity in the roof. In the walls, in a timber frame structure, the walls normally pass outside of the timber frame. And the reason for that is that these posts that support the structure will tend to shrink over time and move. And so you don't want joints to be opening up inside the building. So what happens is you allow the wood frame wall to pass outside where the wood frame wall is at a post, then you connect it to the post to transfer the shear wall loads into the post to go down to the post connector. And if there's not a post convenient to do it, sometimes you have to use an embedded Simpson anchor or something like that. So that's how that is done. And then on the inside, there's usually a 5/8 or 3/4 of an inch gap spacer made out of oriented strand board or something of the like between the timber frame post and the inside face of the frame wall. And that strip goes up the entire length of the post. I wish I had a detail, and I can't sketch here, but I'd show you. But let's say the post is 8 inches thick. Well, that continuous piece of oriented strand board will be about 4 inches wide up the entire height of the post. And so that gives you an opportunity to tuck interior sheathing like drywall or 1x tongue and groove or something behind the post. So as the post moves with change of moisture content, no joints open up. And so that's probably a long-winded answer to the question, but I hope I answered your question. If I didn't, come back at me again.
So you build like a traditional stud wall on the outside that's only connected to this at the post then for your shear walls?
Yes.
Okay. Thanks.
Yeah.
I appreciate it.
Yeah. Now, as I said, if it's interrupted by, you got to look at wall openings, of course, and if there are wall openings in it, you've got to use you may have to use tie downs at the jambs of the openings in addition to the timber frame. But usually you try to find enough shear walls that go from one post to the next in each plane to take the lateral loading. And it seldom do you ever run into a situation where you can't do that. Now, if this was an open pavilion, a completely open structure, then the open pavilion has knee braces in both directions from the post up to the trusses and to the plates. And in that situation, when you have lateral wind load, then those braces take the lateral load. And you seldom would ever need sheathing up in the decking because the tributary area of the wind force going into a frame that has knee braces on it is usually fairly narrow. So you're not looking at a diaphragm shear situation of any consequence. Let's see, we got 53. You want to look at another slide, or what do you want to do, Laurent? I got
You know
20.
what, David, I think up to you if you want to quickly go through another project, or we can also, I think if anybody else has got questions for David in general about his career, about his work, about some of the projects we looked at, feel free to share them. I think we've got a few minutes here. Otherwise, in the meantime, David, go ahead. I think to quickly go through one more project.
Okay. I'll tell you what, before I forget, I want to share something with you guys. Here's can everyone see that contact information? I guess, can you see it, Laurent?
Yeah.
Okay.
Yeah.
So this is my email address, drh@dramy.com. There's the URL, dremy.com. And I want to tell you all a little bit about the Timber Frame Engineering Council, which is part of the Timber Frame Guild. And the URL for the guild is actually, I don't have it correct on here, but it's www.tfguild.org. And on there, you can find a link to the Timber Frame Engineering Council and all kinds of documentation, reports, instructions, example drawings, example calculations in some cases, sample specifications and whatnot. And if you think you have an interest in heavy timber, please come join us. The dues are nominal, and you won't find a greater bunch of guys in the world to work with. I mean, you know, everybody that I've ever met in this industry is super committed to quality. You know, everybody is so focused on doing an outstanding job, and it's unlike any other subcontract trade in the construction industry. I can tell you that because I've been involved in all of them, and it is absolutely, in my opinion, the most outstanding and the most fun. Our conferences are a blast, and there's still so many things that we're trying to learn about heavy timber, and so there's lots of room for innovation and creativity. And those of you that are thinking about working on a master's degree or a doctorate, you'll find lots of topics to explore in the heavy timber guild, or heavy timber industry. But if you have any questions or later something comes to you, please don't hesitate to send me an email or call me at this number. Always glad to help somebody learn something new. So
we've got Helen Watts here who just shared the link to the Timber Framers Guild as well in the chat. So feel free to take a look here.
Okay, great. So with a few minutes that we have remaining, we've got let me show you this. Josh, I apologize. Wait. That's not St. Martin's. Where is it? Huh, hang on. Well, heck.
You know what, David? I think we've got 3 minutes left. So I think for everybody's time, we'll probably just stop it here if that's all right with you.
Yeah, that's fine. That's fine. Yep.
But I think, David, thank you so much for your time. This was super, super cool. I think, we've got a question here from Caleb. And I think, yeah, we'll use these last couple minutes if people have questions in general for you, David. Caleb's asking here, does the Timber Frame Guild have dumbed down courses for architects?
Oh, do they have dumbed down courses for architects?
Yeah.
Listen, all of their courses are dumbed down. I was like, we're all a bunch of dummies just trying to learn from each other. Seriously, yeah. A lot of architects belong to the Timber Frame Guild, and you'll find a number of architects around the country, not too many, but a few that just try to specialize in timber frame architecture, and we think that's great. The biggest problem that I would say we run into in the industry is working with architects who are not familiar with timber framing and then trying to school them into design principles. And you'd be amazed at how many architects and engineers out there don't know how to do a design or even sketch up the concept of a simple working truss. So it's a little bit disconcerting. Anyway, this is Father Martin's chapel, by the way. You can see it on your screen. I just think it's cool because it's got that big hole in there, and there's the thing that connects it all together. And that's the moment connection, by the way, just for the fun of it. I had to throw that in there, Josh. I hope you don't mind.
That's a really cool. And it's all stainless, I believe, right?
All stainless steel, stainless bolts. Yeah. So
Yep.
you guys that are dealing with common lumber, come on over to the timber frame side and do some fun stuff with us.
Awesome. And David, if you don't mind, I'll share my screen again. We'll go over the next sessions coming up, and I think you're in one of them. So I'll just share briefly. Webinars coming up next week. Connor here, or actually 2 weeks from now, Connor will be running a short webinar on designing columns in residential structures. And then the week after that, David is coming back to do another one of these webinars. And this time he'll be talking about commercial buildings. So office buildings, different kind of buildings like that, and the different challenges that brings. And the week after that, we'll also be looking at wind load calculations for residential structures. Some of you might have noticed we've just released our main wind force resisting system load calculations. So if you want to take a look at that, we'll be going more in depth into how that works and what that looks like. And you can find that or sign up at clearcalcs.com/webinars.
And check out the book, Consulting Engineering Success. You'll love it, I think. I promise. I'll refund your money if you don't like it. Don't worry. Go to Kindle at Amazon and download it and enjoy it and tell me what you think.
Absolutely. And I'll just show it again here. And I posted the link in the chat if anybody wants to go and purchase it. Really, I personally, I really encourage you reading it. It was a very enlightening read and very fun to read as well. So
right now it's available as an ebook and we're working hard on getting the paperback up. We're days away from doing that, 2 or 3 days at the most, and it should be up and running as paperback.
There we go. That's awesome. Awesome. And with that, thank you all for attending. Thank you, David, for your time, your knowledge, your insights. Thank you to everyone who participated, asked some great questions, and shared their experience. Josh, in particular, I think thank you for coming in and bringing in your perspective from the construction side. That was really cool. And we'll be running more of these. I'll also add, if you're on here and you're thinking, hey, I've got some projects I think would be cool to show on here, send us an email. We are super happy to discover what everybody is building, because we've all got some really cool stories, some cool projects. And the goal here is that we can all learn from each other and all come out with better work, faster work. And I think, yes, please share if you're interested in this. You're going to get a quick survey at the end here by email, I believe. Please fill it out. It just helps us make better webinars if there's anything that comes to your mind. And as always, you can reach out to help@clearcalcs.com if you've got any questions. And David also shared his contact information. I apologize, I didn't add this to the PowerPoint, but perhaps, Connor, if you want to just put that in the chat briefly so people can write it down. Again, I think you did share it earlier, David, but otherwise, thank you everyone for attending. Well, we'll if that's okay with you, David, we'll include your contact information in the follow-up email.
Yeah, that'd be great. Thank you so much. Thank you all for listening. And I especially want to thank Dan Kaiser. Dan was the designer on the Horizon Community Church. What a great job that was. And so hats off to you guys that are out there doing that great design work, Josh and Dan and the rest of you. Thank you so much for coming.
Thank you all. I wish you a lovely end of your day. Bye-bye.